All right, it is my pleasure to introduce our keynote speaker as we transition and set up all the slides for him. Our speaker is someone who has been shaping internet research and practice for more than 3 decades, both in academia and industry. So Grenville is currently engineering manager at Netflix in Australia, where he leads the R&D on transport protocols. He will share more about his journey and his strong connection to LCN in a second. So we agreed that I will not read from his bio and whatsoever. So yeah, but I want to share one little anecdote. When I invited him, a member of our steering committee, I will not disclose who that was, immediately replied and calling Grenville the role model of LCN, and you will see in a second why that is the case. He was referring basically to the fact that Grenville published early in his career at LCN, and that put him on a trajectory which he will share more about in a second. And yeah, today Grenville returns to LCN, which is great. He will speak on media streaming, application-informed pacing, and coexistence with cloud gaming. And he will share how transport protocols like TCP and QUIC can coexist and how can they be guided with special application needs. So yeah, please join me in welcoming Grenville.
Quick question, you can all hear me? Hands up if you don't. Okay. Thanks. So, maybe I had a clicker that works. Technology.
Try again.
Love it. All right. It's both frustrating and career security, really, isn't it, when technology doesn't work? Yeah, so I promised Florian that he didn't have to talk too much because I was going to talk too much. I wanted to give a brief intro to my connection to LCN, which actually started in 1993. My very first conference as a PhD student, got to leave Australia, flew over to the US, and gave a talk on some really totally cool asynchronous transfer mode research. And now, this is the early 90s, so ATM was kind of cool back then until we realized that it wasn't. I tried my best to help it make not cool because the work I was doing, the paper I was presenting was on how to use Ethernet LANs to carry ATM cells. Because back then fiber was pretty expensive in university labs. We didn't have much fiber stuff, so we put the cells in LAN packets and shipped them around and thought we were very cool. Over subsequent years, so I enjoyed the LCN experience. Over subsequent years with colleagues and students, I was involved with 17 more co-authored papers spread over time. Now, the nice thing about this trip, and this is where it's an opportunity, right? LCN was a growth opportunity. Because I got to fly to the US, I figured that was a great time to also organize a few job interviews. I interviewed at Velcor and at 4 Systems, at BBN, who wisely turned me down because I had a bad day and it really wasn't very good, and up into Canada, leading to this, the career path. I ended up starting work with Velcor in July of '94, and then moved on, did a bit of a time in Bell Labs. Both of those periods were were in New Jersey, then I moved out to California with Bell Labs. The logo that Lucent Technologies had was Bell Labs Innovations, and one of their innovations was to crash just before the dot-com crash. So in 2001, I found myself pondering what to do next. And what I did next, well, actually, no, it was another story. I was blank there, but those of you who are fans of the Apple TV series Severance might recognize Lumen Industries there. I can't tell you what went on in that building. See, that's a joke for all of you. Okay. My outie's not as funny as my innie thought he was. All right, so I came back to Australia after the dot-com crash, decided to come back to academia. I spent 16 years in academia. And started a small research centre at a university down in Melbourne called Swinburne University of Technology. There have been people from Swinburne publishing in LCN over the years, and they still do. A couple of them are here right now. And then in 2017, I had an opportunity to do a secondment at Netflix in their Open Connect business unit, which is Netflix's own internal CDN that we use for delivering content around the world. And in 2018, I decided to jump ship back into industry. And so for the last many years, I've been engineering manager of an R&D team that is responsible for the streaming video, the TCP stack that we use to deliver our streaming video and our live video. And in the last 2 or 3 years, we've been developing a cloud gaming product. So my team is responsible for the WebRTC-based stack that does our low latency cloud gaming video streams. So let's get back onto the actual topic of some interest. And that's the question of, I'll reframe the question, is what if media streaming servers transmitted packets only as fast as needed? Right, there's one sentence and 3 main themes in there. First, what's a media streaming server and why should we care? What does it mean to be transmitting packets only as fast? And what does it mean to be as needed? So the big question I want to dive into is, why is this even a question? Right? And now I think it's an important thing to ask because that then leads on to the rest of my talk. You may or may not think it's an important question to ask, but hey, I've got a talk to give. It's shared networks. All right, they're the problem. We have an internet that has evolved over decades, and people insist on trying to use it for both interactive apps with varying degrees of success or lack of success, and lots of not so much interactive apps, but pushing content, all sorts of things. I don't have to enumerate what they are. But there are bottlenecks everywhere, and those bottlenecks cause packets from everyone's flows to be squished together, and those shared bottlenecks create challenges. So, quick spoiler. I'm going to jump to the end, and then I'll come back and make my way to the end, that if you can paste your TCP connections that are supporting your streaming media, that helps with coexistence with interactive apps. I've got a demo here. This demo video is a cloud gaming fly-through, so we're going to see the video in the bottom left and the top right is of a cloud gaming session, nominally about 5 megabits per second. And then a couple of seconds in, we'll start competing with a streaming video session, nominally 8 megabits per second of streaming video. And what we'll see is in the top right-hand corner, the top right version, you start to get some shuddering. In about a second or two, you'll start to see shuddering effects because of the SVOD interacting in the bottleneck. The bottleneck's 30 megabits per second. So you think 8 plus 5 is less than 30, it should be fine. But what you do see is you see a shuddering that goes on that doesn't actually show up when you paste the SVOD. So by pasting the SVOD at a rate that's acceptable to the SVOD session, we actually got a significant improvement in the cloud gaming session. So that's the TLDR of the talk. I could sit down right now and just leave you with that, and we could ask questions and I could elaborate, but instead I'll keep going. So media streaming is essentially, in the industry today, is Dash-like. Right? Now, none of the companies use precisely Dash. Well, I'm sure there are companies using precisely Dash, but most of us are using some variation. The same basic theme applies. And so those of you not familiar, Dash is dynamic adaptive streaming over HTTP. And the essence of it is that we have both the storage side, the server side is storing content that has been pre-encoded at a whole bunch of different bit rates, creating what we call a rate ladder. And then we've sliced each of those rungs into, for example, 2-second chunks of video. So each of these chunks will be a self-contained group of pictures that carries 2 seconds of video, and we slice it, slice it, slice it. Store them on the servers. We've got high quality levels, mid quality, low quality, all sorts of intermediate levels. And the client is then able to retrieve those chunks in a sequence that makes sense for rendering on screen to stitch them all together and create the show that you want to watch, the episode or an inserted ad or a movie. The client gets a manifest, tells it where all the chunks are, and then the client makes its own decisions in order to get those chunks in the sequence required. Now, the reason Dash postulated the need for multiple rungs is because we wanted the clients to be able to adapt to network conditions. Right. So the client-side adaptation is essentially figure out, based on recent network conditions, I don't know if I'm standing in the wrong space, the microphone's cutting in and out, the highest rung of the rate ladder, figure out which is the rung that's the highest up that I can pull my chunks from and get them in a timely manner, given network conditions as they have recently been perceived. And a timely manner here is, if the chunks are carrying 2 seconds of video, I want to receive that. Pass it off to my renderer, it's being rendered on screen, I need to be able to get the next chunk in before that first chunk has been used. Right? And I'm going to infer network conditions from the time it takes me to get those chunks. Now, the actual delivery of a video chunk, now whether it's 2 seconds or 1 second or 1.5 or 3 seconds, that's very much independent of, there is no spec that says it has to be 2 seconds. It's up to the individual designers of their particular streaming content, media streaming solution. But at the end of the day, the actual delivery of the chunk is not HTTP. It's the underlying transport stack, which will be either TCP or QUIC in most people's implementations. So the under-the-wire behavior is controlled by your TCP stack or your QUIC stack. And we rinse and repeat. So here's another illustration, a little bit of an animation. The GET request goes out to the server. The GET request will be either a range request or a particular file fragment indicating the chunk desired. And then your transport stack, your server, will simply respond by chopping that chunk up into tens or thousands of IP packets and sending them back across the network. Two things of interest here. There's the response time. That's how long it took to actually get the chunk delivered. And then the request interval. So if I've got chunks with 2 seconds of video in them, I'm going to, on average, be requesting a new chunk every 2 seconds to replenish the content that I've already received and rendered. And ideally, what I want is for my transport stack, which is in control of the intra-chunk packet transmission, to get those bytes across so the entire chunk is delivered with a response time that is less than that playback or request interval. Right? And all of this, some of it's in our control. If we're the server operator, the TCP congestion control algorithm is in our control. The network conditions are not in our control, but it all mixes together to affect the response time. Now, I said rinse and repeat earlier, and that's a bit of a simplification. Right? To cope with variations in network capacity, most clients will build up a playout buffer. So they start by simply grabbing lots and lots of chunks, and maybe they'll build up 8 seconds, 12 seconds, 30 seconds, and then start rendering on screen. It's not going to take 8 seconds or 12 seconds or 30 seconds. What they'll do is they'll try and pull down a lot of chunks of data as fast as possible. So you press play, you wait for a little bit, you get a little spinny wheel, and then it starts playing the show. And that's the client building up its playout buffer to at least a minimum sufficient acceptable level. What that level is, Netflix is going to have one level, Disney Plus will have a different level. They'll have their own particular heuristics, and we've tuned them as we think is important, to give you what we consider to be an acceptable or the best playout experience. But this is, broadly speaking, what all the clients are going to be doing. When they get into steady state, the playout buffer has maybe, in the ideal state, might have hundreds of seconds of content. We're chewing through the content, we're pulling chunks out, we're rendering them on screen and replenishing the playout buffer at about the same cadence. But at the beginning, of course, we want to just push stuff in as fast as possible. This animation tries to do what in words I was trying to do. Imagine at the beginning, the playout buffer is 0, we want to build it up. And we build it up by having a large burst of traffic across the network. Now what I've listed there is capacity, that's the network's path's capacity, and the bitrate line is the nominal bitrate of the content itself. Okay, I've got the content, I might continue rendering, the playout buffer drops a bit. At a certain threshold, I'll say, you know what, I need to replenish my playout buffer, so I'll do another burst, another GET request. Maybe I'll do 2 or 3 GET requests, but I'm going to do a little bit more. Let the playout buffer drain as I'm rendering the frames out on the screen. So what you're seeing as the member is just smooth rendering, and what's going on the network is chunks, and then idle time, and then a chunk request, and then idle time, and a chunk request, and so on and so forth. Another way of looking at this is that we've got nested control loops. Right? The client is sitting there deciding, chunk by chunk, where on the rate ladder am I going to get my next chunk from, and why would I do this? So internal player state is going to be taken into account. Measurements we use, the player state internally is often, the player buffer is the main one. Our internal client-side measurements of network capacity is going to be another driving factor. And then we do our rung selection and then decide when are we going to get the next chunk. Right? So nested control loops. The net effect here is that everyone in the community who are building their own clients and server combinations are going to have their own ABR or adaptive bitrate algorithm that makes its own choices along the way. Do I go for the high segment? This particular example, I've got a high quality segment, something happened, the network capacity wasn't what I thought it was, I've gone down the rate ladder to the bottom, then I'm moving my way up the rate ladder as I'm getting successive segments. You, the member, what you see is continuous play out, but possibly the quality is varying over time, and that's what's going on behind the scenes. Now, what matters for the purposes of this talk is that all the on-the-wire behavior, and what does TCP or QUIC doing about it? The fundamental issue that we have today is that TCP is capacity seeking. Right? It will deliver those video chunks as fast as the network allows, not because the client's ABR said so, but just because that's how TCP works. Right? And so we now have burstiness at the interchunk level, the chunk and idle time, and then chunk at idle time. This is macroscopic burstiness, but microscopic burstiness within the chunk. TCP pushing and backing off and pushing and backing off, inducing RTT inflations, because it's capacity seeking. It'll induce RTT growth, it induces additional packet losses that perhaps you could argue you didn't really need to have. So why, right? Why do we find ourselves in this situation? It's not actually a question of TCP versus QUIC. For those of you who know the debate, people are like, oh, there's QUIC is so much better than TCP. And yeah, look, there were innovations, and QUIC certainly has improvements in terms of being able to multiplex different streams over different connections, avoiding head of line blocking issues. It has some refinements in terms of packet loss detection and recovery heuristics, but at the bottom of it all, both of them are designed to do reliable in-order byte delivery as fast as possible. And that's because of the congestion control or rate control algorithms that you're using. Right? You'll have heard of Neurino or Cubic or BBR. Now, the knowledge of the details doesn't really matter at this point. It's that these affect how your bytes get put on the wire, and they can turn up in a TCP stack, they can turn up in a QUIC stack. So no matter which one you're using. Now I don't think anyone has actually implemented QUIC with Neurino, but I believe the original specs actually talked about using Neurino, and everyone just kind of went, yeah, we've got to say that because Neurino is the one that has an RSC, and it's standards track, but everyone does QUIC with either Cubic or some variant of BBR. But that's what's causing the dynamic behavior on the wire. You might want to say, well, why capacity seeking? And it boils down to, I need to automatically adapt to variations in available capacity. If at some point I discover, I'm anthropomorphizing a transport stack here, if at some point I discover that my path gives me 15 megabits per second, I'm cool, all right, 15 megabits per second, I'm going to push stuff. I've adapted my rate, or I've adjusted my congestion control window, or whatever it is I've done to use 15 megabits per second. And then network conditions change. Maybe some competing traffic's gone away, and suddenly that 15, the path is now capable of 30. If I don't continuously seek capacity, I'll never know. The network's not going to tell me. The network has no idea. And so your transport stack has to be capacity seeking in order to ensure it's always making the most of the available capacity. And that available capacity can be fluctuating, so we need to keep pushing. So we go up when it's possible and go down when necessary. And that means we adapt. But the most important aspect of this is that we have to be able to adapt without any help from the network. Right? Now, in fairness, people have proposed over the years scenarios where the network could let us know something. Well, maybe we could do signaling protocols and have guaranteed service, and that's been tried and it wasn't flexible enough. So we are where we are. Over the last 2 or 3 decades, people have built transport protocols that expect nothing from the network, except the network saying too much. So what we do, again, the transport stack, repeatedly push the network, and we push it for a signal. Now, typically, we're looking for those indirect signals. The indirect signal, the classic indirect signal, is packet loss. And I keep pushing, keep putting more stuff on the wire, and at some point, the network has lost my packets. Right? Now, that's a pretty dramatic signal. It says basically, look, you've gone too far. Now, whether you've gone too far by pushing up against a bottleneck speed or you've gone too far by pushing up against a policy implemented by a policer, it doesn't matter. The packet loss says you've gone too far. Now, there can also be variations in transit delay, the delay between putting the packet into the network and it popping out the other end. Right? By definition, with a StatMux-based network infrastructure, every bottleneck has got queues. If you're putting in too much, stuff has to build up in the queue. If stuff's building up in the queue, it gets delayed. And so there are some transport protocols that look for variations in delay as a signal. There are direct signals. So this is one aspect where people have decided, look, the network could tell you something. And that's using ECN, which is and marking your packets for the network to basically say, look, I'm getting close to the point where I'm going to drop it. How about I just send you a mark instead so you can do something smart? Either way, what the transport protocol is going to be doing is increasing number of packets in flight over time, probing for that limit, probing for that signal, trying to push the network, Now, it might be that it's a rate-controlled transport protocol, so they're essentially growing their rate. At the end of the day, we're looking for the network to give us that signal. Then we back off on the signal. We say, all right, we've reached our limit. We back off, and then we try again. Like a recalcitrant teenager. You say, don't do that. It's like, and then they come back and try again. All right? We are going to do that all the time. That's what the transport protocol is doing in order to seek, did the operating point move? Has the network moved? Has it gone from 15 megs that is available to 30? Has it gone from 40 down to 12? We need to adapt, and we do that by continually, cyclically pushing the network, looking for those signals, backing off, and rinse and repeat. The different algorithms that are out there differ in the signals they track and how they respond. One thing that's worth keeping in mind are loss-based algorithms. It's right there in the name. They have to induce loss in order to figure out where their operating point is. So Neurino is a loss-based algorithm. Cubic's a loss-based algorithm. They have to fill your queues. And so as a side effect, they will induce RTT inflation. There are hybrids, like BBR essentially takes a slightly different approach. It says, I'm going to try and estimate the rate at which the network is successfully getting my packets across, and then I'm going to pace my packets out at that rate. I'm looking for that optimal point where I'm using all the available capacity, but just not too much more because I don't want to induce queuing delay. But at the end of the day, BBR still has to seek out and test, has the path moved on? Is the path that gave me 20 megabits per second a second ago, is it now capable of 25, 30, or 60? Well, so BBR also goes into a probing phase on a regular basis where it's just pushing the network a bit harder, over and over and over again. And this gives us packet loss events, regular latency spikes, and that is what we call hilarity. Right? Everyone's sharing those bottlenecks. If I've got one TCP connection pushing the network cyclically, some little voice over IP flow or an old school first-person shooter games control signals going back and forth over the network through that shared bottleneck are going to see latency fluctuations as well. And they may, in fact, end up being collateral damage if some TCP connection is pushing the queue right to the limit, and the next packet comes in as that VoIP packet and it gets dropped. So that's a lot of fun. A bit of a sidebar, packet losses are not necessarily a wonderful thing too for under resource-challenged devices. So a little illustration here. Imagine you've got a TCP connection, you've got your streaming client, it's asked for a chunk, and the server is busily sending packets, and it's got a whole lot of packets in flight. 10, 20, 30 packets in flight, whatever. Sixth packet comes through, and it gets lost. Now, the picture up there is trying to capture the notion that as the first 5 packets went in, they arrived at the client, the TCP said, these are in order, that's fine, I'm going to push them up the kernel, they're going to be available at the socket, the app reads from the socket, everyone's happy. When the 6th one got lost, the packets from 7th packet onwards all get queued up inside the kernel of the client device because they're not in order. And TCP is all about in-order delivery. And so TCP says, well, sure, it's stuck in my reassembly buffer. That's where it's going to be. The app is sitting there going, well, I don't know, something's gone wrong. Everything's gone silent out there. TCP discovers, perhaps dupacks come back or something else, a timer fires, and it discovers there was a packet loss, retransmits the lost packet, gets to the client, gets put at the head of the queue. The reassembly buffer is now full of in-order bytes, a huge number of bytes in order, and the app turns around and does a big read off the socket. And we've noticed that some of the really low-end devices actually will shudder and stutter a little bit because the CPU, a little burst of CPU activity pulling bytes out of the kernel is enough to cause the renderer to just skip a little. So anyway, amusing sidebar. Now, it's not entirely true to say that networks can't help. Right, so I do need to acknowledge that the networks, and this goes back to at least the mid-90s, when random early detection was first being developed, and proposed this notion that the network can provide an early signal. Could think of it as a defensive early signal to these transport protocols that are looking for a signal, and the network says, well, look, based on my queue occupancy here, I see my queue is starting to grow. I sense that I'm going to be pushed, so I'm going to start giving you early warning signals. I'm going to start dropping, maybe not dropping every packet, but dropping some statistical, probabilistic selection of packets, and hope that on average the transport protocols that are currently pushing through that bottleneck will back off earlier than they would have, and everyone gets a steady state where the queue occupancy is lower than it would have been. Right? And these general class of active queue management schemes are generally used to trigger the ECN marking that I mentioned earlier. So they could either be dropping your packets proactively or marking your packets proactively. But that's network support for creating less queue occupancy in response to these capacity-seeking transport protocols. Another technique that is often used in combination, and you'll see that in the FQ part of FQ-CODL, is distributing the flows across queues. If you come up with some hashing function that says, let's separate out the flows across dynamically established and collapsed queues on demand, we can schedule amongst the queues, spread the load around, keep the queue building flows isolated from non-queue building flows, and maybe that's deliberate, maybe that's just simply by accident. And then apply your active queue management strategies to the individual queues themselves. Right? Now, again, that's another 2-hour seminar on just AQMs and the different variations and what does L4S mean and why is that different from FQ-CODL, and I'm not going to go into that. Suffice to say, the networks can help. And we've got flies. Excellent. It's fair to say that the industry deployment of AQMs is a work in progress. It's also fair to say that I don't want to say much more than that. It's a work in progress. So, different countries, different ISPs, you will find different degrees of AQM being rolled out, but it is happening. So what's the only as fast as mean? This is where we start talking about packet pacing. And by we, I mean I'm going to start talking about it and you're going to decide whether or not it makes any sense. So pacing is about two things, a rate limit and a kind of a sense of smoothness. And I can say a rate without a time window isn't very helpful. I can say I'd like you to send me data at 12 megabits per second, or 10, or 15, but if I don't specify a time period, then how is that useful? I could be over a minute, and I could do it all in the first millisecond and then just wait for a minute and go ta-da. Or I could spread it all out. And the spreading out part is what really matters here. Partly it's making sure that your rate limit, for the purposes of this talk, it's about doing pacing within the lifetime of a given chunk. Because right now, those chunks are being delivered by TCP that doesn't care. It just goes as fast as those acknowledgements are coming back. If they're successfully delivering packets, I'm going to keep going. So here's an example of what I mean by the time period and how it matters and smoothness versus burstiness. So I've got 3 different ways of doing 12 megabits per second I'm going to show. One of them, let's imagine I have 100 Ethernet frames and I send them all in a burst, and then 100 milliseconds later I send the next burst of 100, and then 100 milliseconds later I send another burst. That's 12 megabits per second, or close enough. I could also do that by sending 10 packets and wait 10 milliseconds, 10 packets, 10 milliseconds, rinse, repeat. And that's also 12. 12 is also 1 packet every millisecond. Which one of these is pacing? If you haven't specified a burstiness, then all 3 of them are. Right? I've got a pacer that has a 100 millisecond timer that fires. Every 100 milliseconds, a timer fires and tells me I'm free to now release my next lot of bytes, and I'm going to send 100 of those packets because that's how I get my 12 megabits. In the most extreme smooth version, I need a timer firing every millisecond. And that's actually at the core of why you haven't seen TCP pacing being used very often. Right? You go back 30 years, and your CPU was busy enough as it was, just getting packets across the bus and doing this and doing that, and having timers firing every millisecond would have just blown its little brain out. It just wasn't feasible. Most of our protocol designs were based on it being event-driven. Right? I'm not doing anything. An ACK comes in, then I do stuff. An ACK comes in, then I do stuff. I'm triggered by events, and the events will happen as fast as they happen. I'm not going to have timers firing all the time on 10, 20, 30, 100, or 1,000 parallel TCP connections, all with slightly different timers. Not going to happen. Today, it becomes much more viable. So the benefits we get, if we were to pace our TCP traffic at below the bottleneck speed, we essentially eliminate gratuitous queue growth. If we were to pace below bottleneck speed, we eliminate that queue growth, which then eliminates unnecessary packet loss. If we spread out the packets, it increases the chances that our traffic will interleave in amongst the traffic from other sources that are also sharing bottlenecks. I got a little lab experiment that I ran to illustrate some of this. Imagine I have a TCP connection doing chunks every 2 seconds. I send a block of bytes that takes about 1.2 seconds or so to deliver through a 10 megabit per second bottleneck. So the conditions are listed up there. Turns out, not surprisingly, that the dead air, actually sorry I skipped a bit there, in parallel with the TCP session I've got a little UDP flow going, 80 kilobits per second, approximating a very trivial voice over IP codec, putting stuff across the wire. And I'm measuring here on this graph the one-way delay experienced by the voice over IP flow through that bottleneck. Between the chunks, there's nothing going on. There's no competition because the TCP connection is idle. It's completely quiet. The VoIP's going through. And then as soon as I send TCP starts sending the chunk, if it's unpaced or it's paced at a rate above 10 megabits per second, and I've got a couple of colored lines there for 11 meg and 16 meg, and the dark blue one being unpaced, they all start inducing queue occupancy fluctuations. And the voice over IP flow experiences those same variations. But when I'm pacing the TCP connection at 9 megabits per second, just below the bottleneck speed, the VoIP flow experiences very little fluctuation. There's a slight variation here. You can see, what you can see there, that slight angle is because I was actually sending, in this particular demo, I was sending 2 packets at a time. And I was pacing it out with a little burstiness of 2 packets. And that added in about 1.5 to 2 milliseconds of queuing delay. If I've got a paced flow competing with unpaced flows, in this particular case, the unpaced flows are always going to push your bottleneck. So there's a limit to what pacing can do. If I paced my flow, but there's a whole bunch of other people going through the same bottleneck and they're doing capacity seeking, you know what? They're going to push the bottleneck. They're going to induce queuing delays. They're going to induce RTT fluctuations. There's not much I can do about that, but my paced flow, because of the interleaving, is going to see less packet loss over time. So that can be useful too. Nothing I'm saying in this talk should be construed as, hey, we've invented pacing, it's a really cool idea, you should all try it. Pacing in various forms has been around for a long time, and a number of different companies have been implementing some form of packet pacing capabilities into their operating systems. Michael Welzel from the University of Oslo last year started trying to pull together some words from a number of different places, a number of different co-authors to create an internet draft that tries to capture the state of the art of where are we at with pacing capabilities in the FreeBSD operating system into Linux and iOS. So worth having a bit of a read. Just Google that and Michael Welzel and you'll get that draft. So what are we missing? At this point, there's the question of, well, what should that rate be? Right. The part where I stated, as needed. Right. That is where we need the application to tell us something. We're the transport stack, and we're going, well, okay, I can pace if that's what you want, but what exactly do you want me to do? And that's something that we've been calling, or myself and my colleagues have started calling application-informed pacing. So we're not pacing the GET requests, we're pacing the TCP packets that get emitted back to us because of those GET requests. This was first articulated publicly in a SIGCOMM 23 paper called SAMI, and it was led by Bruce Spang, who was a PhD student at Stanford at the time, and he's also collaborating with us inside Netflix, and now he works with us. And the essence of SAMI was this, that for every chunk, the client would establish its own definition of a sufficient TCP delivery rate that would allow the client to achieve its own goals. The ABR had a certain set of goals, and then pass that information back along with the GET request, and the server would honor that by ensuring that it would send out the TCP segments no faster than what the client had requested, regardless of what the network was capable of at the time. So essentially, we're kind of curtailing TCP's typical capacity seeking behavior. We've implemented this and are running experiments to sort of figure out where's the best way to deploy it. Our implementation is that TCP can still do capacity sensing such that if the network path is giving us 10, we've requested a pace rate of 15, well, we'll go at 10 because that's, the acts are not coming back fast enough to justify anything better. But if the path is good for 30 or for 50 or 100 megabits per second or higher, and I'm talking about the path being dominated by the last mile into the home, and we've requested a 15 megabit per second pace rate, well, that's what our servers will do. We will pace it out at 15 megabits per second. And so this idealized way of doing things today becomes a slightly different idealized. So in the extreme, we would fill our playout buffer unpaced, and then once we start to replenish those chunks, we request a pace rate that's basically the rate that the video needs to be delivered in order to maintain our smooth playout on screen. Now that is hugely idealized because it's not going to be enough, right? I've forgotten all about the playout buffer. And I've forgotten about network variability. I can't just replenish it just at the speed. Just in time delivery is nice, and it might work for, you know, shopping centers and wholesalers and factory warehouses, but it's not so good for doing glitch-free streaming. But none of this would actually work if it wasn't for the fact that over the last decade and a half or so, the available capacity on typical paths from servers, from CDNs out to their customers has skyrocketed. Now, these numbers I got from a colleague represent the US, kind of approximate US numbers, going from 5 meg to 200 meg, you know, we're seeing on average. And in that same period of time, our top video bit rates, the encoding rates for our videos, have grown very, very slowly. Even as TVs have gotten bigger and the resolutions have gone up, there's been a whole bunch of fascinating work that is far more complex for my little brain to understand in the encoding space. The H.264 encoders, 265, AV1, all these things, they're doing incredible things with compression, such that we can do 60 frames a second, very high resolution graphics, and yet we're sitting there around under 20 megabits per second. And in some cases, you know, the next generation of codecs come out and the rates actually go down for the same quality. It's pretty cool. At least I think it's cool because I don't fully understand it, right? And I guess that's the very definition of cool tech, right? It's when you don't understand it, but it does something nice. Now, we see approximately, you know, 13 times, right? We're going to see our bit rates that we need to deliver are exceeded by our member average throughput substantially. So we're in a situation where pacing at what we need will often end up with us pacing at a rate below the bottlenecks along typical paths. So the ideal pace rate is going to be something that's above your video delivery rate and below your network bottleneck speeds. Now that's the ideal. You can't always know what the bottleneck speed's going to be. It might be intrinsic to the tech of your link layer. Maybe it's DOCSIS. Maybe your ISP's got you on a 200 meg down and a 20 meg up plan, or maybe you're on a 50 meg down and a 5 meg up plan. That's something intrinsic. When you get competition, the available capacity changes again. But this is ideal. If you go too slow, you can starve the playout buffer. And if we can't get those chunks across in time, then you need to move down the rate ladder. But if you pace too slow, you can also starve the client's ability to know when to go back up the rate ladder. Because the client is now seeing your pace rate as the apparent available capacity on the path. It doesn't know anything else. It's seeing the chunks coming across. It knows the size of the chunks because it asks for them. It has a manifest. It tells it the size of the chunks, how many bytes are in each one at each quality level. It's getting them delivered. It goes, oh, the network's giving me blah. Now, obviously, a smart client would be like, it's giving me 5 because I asked for 5. Who knew? But it's a complication. And if you pace too fast, then at some point, you might just ask the question, why am I bothering to pace at all, right? If I'm pacing so fast that I'm exceeding the bottleneck speeds and I'm really not going to get much reduction in RTT, I'm not going to reduce the queuing delays all that often. So we want to sit the pace rate somewhere in this optimal range. And for those of you looking for research questions, things to embark on, this is what's known as an R&D opportunity because there is no single answer. There is a spectrum of possibilities that depends on your particular ABR algorithm that you're using. And some companies will have their own internal decision-making process about what they want to optimize and where they should choose their pace rates and what they are willing to trade off. And researchers can grab open source Dash implementations and do their own experimentation and figure out, come up with their own heuristics and trade off various quality of experience metrics against what you'll see on the network and the improvements you might get in RTT, for example. So as a way of illustrating this, what if I had I've got a graph here, a video buffer occupancy across the x-axis and my pace rate selection. I might want that to bounce around. As my player buffer gets full, I can afford to pace more aggressively. As the player buffer drains, I might decide to pace at a higher rate. What I meant by aggressively, I meant pacing lower. I could just pull out of thin air a number that says, oh, let's pace at 2.5 times my video rate when my player buffer is full. But when my player buffer is empty, I want to go faster. I want to replenish the player buffer, so I'll go at 3 times my video rate, 3.5. Now, I've just pulled those numbers out of thin air. This is not a number that we're particularly using at Netflix for our experiments, but yeah, we could do. Because either of those still sits substantially below the the types of good throughputs that we see on average on our paths out to our members. So this is a win. But whether that's a nice gradient, whether the buffer empty paste rate multiplier is 3.5 or 4 or 6 or 12, and maybe the buffer full is down to 1.25, it's up to you. It's up to us. It's up to anyone who wants to dive in and do some research in this space. Whether that's a nice linear curve based on the top video rate or the next rate up the rung ladder or your current chunk size, maybe you decide to do something like, you know what, my current chunk is this many bytes. It's got to go in 2 seconds. I'm going to do a delivery time-based pace strategy where I will just pick a pace rate that ensures that whatever the chunk is, it will always be delivered in, say, 1.5 seconds, or it will always be delivered in 70% of the time of the video that's encoded in that chunk. There are various different possibilities here. As I said, an R&D opportunity. There are no fixed answers just yet. So, what have we seen? Now, I'm going to be really vague here, because that's the only way I could get our PR and comms people to allow me to give the talk. So no absolute numbers. Not surprisingly, you know, when we've rolled out, and of course we've been tuning different parameters and trying different things, so I'm kind of creating a hybrid of some diverse set of experiments here. Not surprisingly, our instantaneous throughput, like the bursts, the speed at which individual chunks are being burst and downloaded, has dropped between 60 to 85%. I've seen that. That's kind of cool. It just tells me pacing is actually working. Is it doing anything useful? Well, we actually see retransmission rates dropping between 35 to 50%. We're still obviously getting retransmits. I mean, there's some signals happening. And round trip times. So for the connections where we're doing pacing, we've measured the RTT that the actual, our TCP stack measures its own RTT, does its own RTT measurements, and we're seeing the RTT times going 30, 35% down. Now, if, you know, this is 35% off a base RTT of 15 milliseconds down to 10, you might think, well, you know, that's no great win. But in the real world, you know, we'll see RTTs. That's both path delays plus the self-induced queuing delays that we typically get when we're doing capacity-seeking TCPs. We might see them drop from 100 and drop by 30 milliseconds, or go from 150 or 200 and drop by a proportional amount too. So you're getting substantial real-world amounts of milliseconds being shaved off the latencies that other traffic is going to experience. And so the key is here the coexistence part. Right? Network latency has been a known issue for some time. It's been a hard problem for a long time. Right? One example, Stuart Cheshire from Apple, way back in '96, I think he was still at Stanford, just starting to contemplate a future life at Apple, put a blog post out back before blogs were even a blog, arguing that latency was the consideration, not throughput, to get good experience on the internet, both for just any kind of apps that involved interaction, and apps, you know, whether it's button clicks and getting the responses back, or genuinely interactive, like video conferencing apps or online games. Speaking of online games, so back in 2001, in a bit of my misspent youth, and this is partly the dot-com crash, right? So I had a bit of free time on my hands for a couple of months. And so, I don't know, just curious about the latency sensitivity of first-person shooter games. So I set up 2 Quake 3 Arena servers, one in London, one in California. And what was interesting is that they were identically configured, the same map rotations and stuff. And those of you who vaguely recall Quake 3 Arena, like these first-person shooter games, you get lots of players on. They run around for 5 or 10 minutes, 15 minutes, having a game around, shoot each other as much as possible, get frags, the kills, and then the winner is declared by whoever had the most. What's interesting here is that if you look at the y-axis, you can see this. Well, you can just see a distinct curve, line. Sorry, the frag rate. Number of frags per minute dropping off noticeably as the ping time out to those clients increases. So if you're at 50 milliseconds away from my server, or 100 or 150, you see a degradation in your effectiveness. And you might look at the y-axis and go, well, that's only 0.25, it's a quarter of a frag per minute, who cares? But if you've got a 10-minute round and you're a competitive player, that quarter of a frag per minute, that's a couple of frags, you're down, you're not winning the game. And so latency has been an issue. And I mean, the gamer community has known this for decades. So now, in more recent times, the cloud gaming has added an extra wrinkle. We not only need things to be interactive in the sense of your controller button presses need to get back to the server quickly, the server is now streaming actual video back at you. not just sending control messages back and having a local client do the rendering, which is what we used to do for online multiplayer games. So this brings us back to the fact of the little demo that I did at the beginning. Because you just know, if you've got an online cloud gaming service, someone's going to try playing in one room of the house and streaming a movie in another room of the house. It'll be different people, obviously, you know, but someone's going to do this. So what happens? Is this where application-informed pacing helps? This is the background, this is the visual of the little demo setup I had earlier. So I've got your RTP stream, around about 5 megabits per second, going through a 30 meg bottleneck. The SVOD is streaming synthetic content at about 8 megabits per second, not paced or paced. And we've done this. We'll do it again, just to reinforce it. Top right-hand corner, the cloud gaming stream is competing with some SVOD that's unpaced. The bottom left-hand corner, the cloud gaming stream is competing with SVOD that's been paced. Paced to sit below the bottleneck speed. And you can see that the pacing is a win, right? If I pace my SVOD, my interactive apps are going to have a better experience. Now, the particular example here is cloud gaming, but this would apply to any interactive app that happens to be trying to coexist, and this applies. So the general takeaway here is that if the community starts exploring better ways of applying TCP pacing to the delivery of chunks for traditional streaming media type services, we think that there's a very positive impact that can have, potentially on the actual streaming media itself, because low-end devices will see less stuttering of the renderer, but certainly for interactive apps that have to share that network with us. There's a lot more here that could be talked about. I've been told I have 5 minutes, and that was like 2 minutes ago. So luckily, this is kind of take this as a given, and we can have questions. I've got to the end, basically, but the last thing I want to do is acknowledge there's a long list of names in there of colleagues at Netflix that have helped to get us to this point, to be able to confidently say, yeah, we can actually do this, and other companies can do this, and you know, we've got some stuff and it's showing goodness. There is more. We didn't invent pacing, that's for sure. Application-informed pacing, sure. We're pushing that, but the underlying TCP pacing, that's a community of people predating our work. And a particular shout out, actually, I should say that in the FreeBSD stack, the FreeBSD developer Randall Stewart did the original implementation of what allows the FreeBSD stack to now do TCP pacing for this kind of thing. Having said all that, I'll stop. Or ask any questions. Do we have time for questions? Cool.
So we certainly have some time for questions. Please, there are questions. Okay. Shall we try?
Wow. Thanks, Grenville. Highly appreciated. Just a very simple and stupid question. What is the ratio of a steady state situation in such cases compared to the complicated state situations? Because you mentioned initially steady state is blah, blah, blah. And how often is that the case? Because there's so many activities going along in a network, not only back home. And I would like to understand how important you feel that is.
You mean the steady state of the SVOD stream, or just the steady state of the net? So the steady state I think I was referring to is more that if the client has filled up its playout buffer, and then it gets to a point where it says, look, I've got enough in my playout buffer, I'm just going to now get new chunks just simply at a rate that replenishes what I'm consuming out of my playout buffer. So the playout buffer is being consumed in order to feed the renderer, in order to put stuff on screen. You know, if that's consuming chunks every 2 seconds, I just need to replenish either every 2 seconds, or maybe I do 2 chunks every 4 seconds, or 6 chunks every 3 every 6. That sort of thing is the steady state I was thinking of. On the network itself, I have no idea what constitutes steady state. There isn't one.
Okay, the view of the end system. Thank you.
Hi, thanks for the talk. If I got it right, you said that one of the important challenges is to know how much the application needs, so the video application, right? Are you nowadays also considering the type of device? Because there's a tendency that these little smartphones try to get whatever kind of full HD or whatever kind of video and adapt that anybody is able to see the difference. Because if there should be a difference streaming on a on a big screen and just a smartphone. But is this implemented that you're taking into consideration the kind of device your client is streaming to and then reducing the rate?
Yes.
Can you tell us details?
No. But that's absolutely correct, right? That if you've got a device that can only do up to a certain resolution, then don't ask for the higher resolutions. If you've got a device that, the limitations are taken into account, and that's part of the whole, what does the application need? And going into the details gets into secret sauce, which gets me into trouble. So you can just take it as a given that each company is going to have their own secret sauce as to how they choose to, how their client chooses to behave when it discovers it's on a smart TV versus a games console versus a low-end Android phone. They'll all have their own tweaks to then decide. And those decisions are then going to influence where on the rate ladder they're pulling content from, and those decisions are going to affect what they might do in the future in terms of requesting a particular pace rate if they were to start implementing application-informed pacing, yeah.
Another question?
Oh, whoa. So I want to ask, what about the coexistence between paced and unpaced flows at the same time?
Yeah, look, there's what's that old saying? There's no such thing as a free lunch, or there's no silver bullet, all these kind of euphemisms that basically boil down to, if you've got a shared path and your flows are using pacing to try and minimize your effect on the path, and there are other flows coming and going that are doing traditional capacity-seeking behavior, then in a sense all bets are off. Right? The bottleneck queue is going to be pushed up and down, it's going to drain, it's going to grow, it's going to drain, and so everybody's going to experience these RTT fluctuations. One of the things that I had seen, one of the graphs that I showed earlier, is that there is a chance that your paced flow, if you're smoothing the packets out nice and smooth, the paced flow might experience less packet loss, because there's a greater chance that you're going to interleave in amongst the queue overflows being caused by those other capacity-seeking flows. But if at any point, if you're coexisting with queue building behavior or capacity-seeking flows, then life isn't going to be great. We can't pace our way around somebody else deciding to push the network hard. We've just got to kind of hope that as you get out towards the edges of the network, the likelihood that one home bottleneck is actually being hammered by multiple capacity-seeking streams at the same time, it's lower than perhaps somewhere in the core of the network is going to get hammered by multiple of these things, but the bottleneck's out towards the edges. At this point, I'm just talking for the sake of talking, because the bottom line is, all bets are off in many ways if you've got capacity-seeking flows competing with you at a bottleneck. At that point, that's where your bottleneck, it would be nice if it was doing something like FQCODL, where it was automagically fanning the flows out into separate queues and then round robining amongst those queues and enforcing a kind of a bit of bandwidth sharing and isolation. But again, that turns into the next 1 hour talk that I haven't got ready yet.
Great. I think you were first.
Thanks. Very nice talk. Thank you very much. Tim Strayer, BBN. I think I can set you up if you're still looking for a job. My question is the work that you're doing, would it benefit Netflix if other streaming services were also pacing, or is this a proprietary advantage?
I would phrase it as it would benefit everyone if all the streaming services started doing pacing. So I'm not speaking out of school by saying the following, because one of my colleagues, TY, said this at the IETF meeting in July, that we're already having some conversations with YouTube about, we talked to them last year, we said, hey, we're doing this cool thing, and they were like, and then more recently they've gone, hey, yeah, that is kind of cool, and so we're actually, we're trying to get people interested in doing this, and there are some projects happening in collaboration with some academics in the US who are then exploring that question of, if YouTube does some pacing and Netflix does some pacing, how much benefit can we all get? So yeah, that's the answer at this point.
Yeah. Ho Chi, University of Texas at Arlington. Yeah, thanks for the very nice talk. Yeah, you haven't talked about the queuing effect, the buffer size. I expect if the buffer size is big enough, then pacing will become less important, right? So how the buffer size will have an effect on the effectiveness of pacing?
You're thinking of the playout buffer in the client or the buffer at the bottleneck in the network?
For example, if I have infinite amount of buffer, then you don't need the pacing, right? You just keep sending the chunks whenever you need it to make the buffer enough chunks in the buffer so that you never have the problem of playback jitter or anything.
Yes, I mean, if you had a client with an infinite buffer, and when you press play, it starts buffering up, then starts rendering after it's got about 8 seconds or 12 seconds of video, and then it's playing out slowly, and in the background you're just capacity seeking, sucking the whole thing down from the server into your client. Yeah, you could. Now, I would argue that you probably still want pacing though, because while you're doing that, while your client is doing back-to-back GET requests for the next 30 minutes or 25 minutes or 15 minutes and downloading almost the entire movie, you are smashing the bottleneck, the network bottleneck on your home broadband router, for example. And so any interactive apps that we're trying to run, so someone else in the house is doing cloud gaming or doing Quake 3 or doing Zoom call is going to scream at you. They're going to be like, no, do not do this. And so there's that aspect. There's also the aspect that people tend to pause, or sometimes they'll play the first couple of minutes and then you go, oh yeah, the kettle's boiling, I've got to go off, and maybe I'll switch off the TV. And if the TV has downloaded 30 minutes worth of content and you only play the first 5, then that was kind of, in a sense, waste. Mm-hmm. So we do want to make sure that we're downloading enough into our playout buffer that we can cover for, someone 20 seconds or 30 seconds network outage. But we don't want to have an infinite, we simply can't anyway, but we can't have an infinite playout buffer anyway, because most of your smart TVs have got limited RAM in them. There's practical reasons why that's not going to happen, but there's also just, we don't want to download content that we're not going to use. And if someone says, oh, I've started this movie and then I watch 5 minutes, and I start the next movie and I watch 5 minutes, and start the next movie, I watch 5 minutes. If I've downloaded 30 or 40 or 50 minutes of each of those movies into memory and then have to try and save that for the next time the app starts up, that just becomes a nightmare. So, sorry, I'm talking again too much. The simple answer is we don't. Yes, you would still need pacing, because if you're filling the playout buffer, you're doing it with capacity seeking TCP, and that's going to slam the bottlenecks on your network path. Yeah.
All right. Last question.
Hi, I'm Hiro, representing Computer Scientists. So that's really awesome keynote. And I'm curious. I'm wondering about the standards, because IEEE and IEEE Com Society are making a lot of standards, particularly in the area of computing, networking. So is there any ongoing activity to standardize such pacing or?
Not standardization, not really. I mean, at this point, myself and some of the people on that screen there, and some similar people in YouTube, for example, and there's other companies that are starting to look into this overall space more in the IETF context. So I think it's still new enough. We're figuring out how. Part of it is standardization. There is an opportunity to standardize perhaps the syntax, how do you pass that message back from the client to the server. Right? And there are various mechanisms that do exist in HTTP headers. You can add new headers, or you can just encode things in a certain way. But the real R&D area is going to be that choice of what pace rate do you choose at any given point in your client's life cycle. Mm-hmm. If the player buffer is shrinking, is it growing? Am I up this far up the rate ladder? Am I down or in the middle? What's the optimal pace rate? We are so far from any kind of standardization, and it's not even clear that you'd want to standardize that. That might be just one of those secret sauce things that different people's client behavior behaves differently. So not a comprehensive answer, but that's the answer that I can give.
All right. Unfortunately, time is running out. Grenville will be around still. He even has a paper and a poster, so approach him and continue the discussion. Other than that, please thank Grenville yet again. And of course, we have something for you. So, first of all, a little certificate of appreciation for your contribution to LCN. So thank you very much. And also a little something, a journal and a pen for your next ideas with Aboriginal artwork. So you're
beautiful.
also supporting local community for that. So thank you again.
Thank you very much.
Thank you for being here. All right, and that concludes our plenary session now. We have coffee outside, and then afterwards we will reconvene for our Best Paper Award candidates here in, I think, 30 minutes-ish. So, yeah, enjoy yourself and see you later.